Okay, let's review how to find one-sided limits. There's a few different examples. Let's say that we're looking at one. I'm going to draw a couple of these in here. And in all of these cases, we're going to look at the limit as x approaches 1 from both sides, from the positive, the negative, and then in general. So what happens if we get a case like this? We'll call that 2 and we'll call that negative 2. Well, in this case, the limit from the left or from the negative side would be positive 2. The limit from the right would be negative 2, which means that the limit as x approaches 1 does not exist. And then you're also going to be asked to find the function value. In this case, the function value of 1 would be negative 2 because that's where the colored in circle is. All right, we also might have the point where we have a hole there. The graph goes through it, but then we have a point somewhere else. So in this case, the limit from the left would be 2. The limit from the right would be 2, which means that the limit in general would also be 2, but the function value itself is down at negative 1. So again, the limit does not matter what this point is. The fact that it's at a different spot, it's only about where the graphs are getting closer and closer to. All right, we also might have a case where we have this weird looking function where we have different functions on both sides. So as we approach 1 from the negative side, that would be 2. As we approach 1 from the positive side, that would also be 2. And then as we approach 1 in general, that would also be 2. And then finally, the function value itself, in this case, is also 2. Even though they're two different functions, again, they're both approaching the same spot. So because they're approaching the same spot and that spot is the same, all of these values would be the same. All right, so in these examples that we're going to do, that's what we're going to need to see, is we're going to need to find what the graph looks like and then determine what is happening. So we don't really care about most of everything else. All we care about is what's happening kind of right at just that spot. So we don't really need to know what the rest of the graphs look like, just kind of locally what's happening. All right, so in example 1, first thing I'm going to do is I'm going to graph. Like I said, we're going to have this split at negative 3. That's where our graphs split, and if you can tell, that's where our limits are asking about as well. So again, I don't really care about what's happening with this quadratic. I just really care about where it connects at 3. So when I plug in a negative 3, I get negative 9 plus 30, which is 21, minus 24, which is negative 3. So when x is less than 3, it connects at 3 with a closed circle, and then is some quadratic that opens down. Again, I don't really care because I just need to know kind of how it connects at negative 3. And then when I plug in a negative 3 on the other function, I get negative 6 plus 3, which is also negative 3. That would be the open circle, but it's closed in by the blue dot. With a slope of 2, again, doesn't really matter. So as you can see, in this case, the limit from the left, the quadratic side, would be negative 3. The limit from the right, the linear side, would be negative 3. Because those are the same, that limit is negative 3. And this is one of those cases where the function value is the exact same as both. So again, all I need to know on the graph is kind of what's happening as we get closer to just that spot. All right, let's try example 2. Let's draw this. This time we're at negative 1 is our break point. Again, as you can see on the limits, that's what we're looking at. So when x is less than negative 1, I have a linear function. When I plug that in, I get 1 minus 8, which is negative 7. So I'm just going to throw a negative 7. Closed circle. And it's a negative slope. So it looks like that. In the quadratic case, I get negative 1 plus 4 minus 4, which gives me negative 1. So again, an open circle and a downward facing parabola doesn't really matter. So from the left side of negative 1, it gets closer to negative 7. From the right side, it gets closer to negative 1. Because those are different, the limit does not exist, and the function value is where the closed circle is, down at negative 7. All right, pause your video at this point. Try examples 3 and 4. All right, similarly, in this case, this is another example where they connect at the same spot. So the limits are all negative 1, as well as the function value is negative 1. In example 4, they connect at different spots. So the limit from the left is negative 2. The limit from the right is 0. Those are different, which is why it does not exist. And the function value is the closed circle, which would be that negative 2. All right, the last two types of examples we're going to look at are absolute value functions, which are, in their own way, piecewise functions. So let's take a look at the first one, example 5. We've seen this before when we were looking at the tables. I don't know if you recall, but just to give you an idea, if we look at a table of these function values, negative 1 is where it kind of makes a change. So let's try negative 3, negative 2, negative 1, 0, and 1. Let's plug those values in. And let's see what we get for f of x. All right, so when I plug in a negative 3 here, I get negative 3 plus 1, which is negative 2, but the absolute value makes it positive 2. So I get a positive 2 divided by a negative 2, because those are the same thing. That's a negative 1. And negative 1 times 3 is negative 3. When I plug in a negative 2, I get this is negative 1, and this is negative 1. I'm sorry, that turns into positive 1, though. So it's positive 1 over negative 1, which is negative 1, times 3 is negative 3. So as you can see, all of those values that are going to be less than negative 1, those are going to cancel out but make a negative 1. And negative 1 times 3 is negative 3. When I plug in a negative 1 itself, on top here, I get zero divided by 0, which is a whole, which means it's undefined. And then everything on past that, both of these are going to be positive, so that's just going to be 1, and 1 times 3 is always going to give me 3. So again, negative 1 is my break value. When I'm less than that, I connect that negative 3 with an open circle because it's undefined. And on top, I'm going to get positive 3 with an open circle moving that way. And this is how these graphs are always going to look. So looking at the limits, the limit from negative 1 from the negative side would be negative 3. From the positive side, so that was from the negative side. From the positive side, it gets closer to positive 3. Because those are different, it does not exist. And the function value itself at negative 1 is also undefined. All right, and in example 6, we have a little bit more of a straightforward type of problem. We just have to remember how to graph these piecewise functions. So normally, the parent function is just the v-shape with the vertex at the origin, and then we just have to shift these around based on what it says. So this minus 3 means we're going to shift it to the right 3, and this plus 4 means we're going to shift it up 4. So we're going to go right 3, up 4. And that's where our vertex is now going to be. And because there's no value in front, the slopes of these lines are 1 and negative 1. If there was a 2 there, then the slope would be 2 and negative 2, and so on and so forth. And if there was a negative value in front, then that would be flip it and point it down. All right, so this is a case where both of these kind of approach the same spot, and the function value is at the same spot. So all of these are the same, and they're all going to be 4. The limit from the left is 4, the limit from the right is 4, the limit in general is 4, and the function value itself is also 4. All right, so your turn now. Go ahead and try examples 7 and 8. Pause your video. All right, in this case, example 7, those roads lead to positive 4 and negative 4, which means that the limit in general does not exist and the function value is undefined. And then finally, in the last example, it's been shifted to the right 5 and down 3 and flipped with slopes of 2 and negative 2. But in any case, the limits always go to